We often perceive time as a relentless river, flowing from the past, through the present, and into the future. This intuitive understanding, however, faces a profound challenge when we delve into the realm of physics, particularly Einstein's theory of relativity. Physicists, through the lens of relativity, have come to view the past, present, and future as an illusion, a construct of our perception rather than an absolute truth of the universe. This startling revelation arises from the fundamental shift in our understanding of space and time. Relativity merges these two seemingly distinct concepts into a unified entity, spacetime. Spacetime is not merely a backdrop against which events unfold, but an active participant in the cosmic drama. Imagine a vast, four-dimensional fabric where space and time are interwoven. This fabric, warped and curved by the presence of mass and energy, dictates the paths of objects and even the flow of time itself. This unified framework of spacetime forms the bedrock of relativity and compels us to reconsider our everyday perception of time's passage. This new understanding of time, as we will see, has profound implications for our understanding of the cosmos, from the behavior of stars and galaxies to the very nature of causality itself. Before delving into the implications of relativity for our understanding of time, we must first grasp the revolutionary concept of spacetime. Imagine a traditional graph with two axes, one representing space and the other time. This simple visual aid captures the essence of spacetime, albeit in a limited two-dimensional form. In reality, spacetime encompasses three spatial dimensions: length, width, and height, alongside the dimension of time. This four-dimensional continuum is not merely a convenient mathematical tool, it represents the very fabric of our universe. Objects do not simply move through space, they trace out paths or world lines through this unified spacetime. Einstein's theory of relativity revealed that spacetime is not static or absolute. It is a dynamic entity warped and curved by the presence of mass and energy. This curvature of spacetime is what we perceive as gravity. Just as a bowling ball placed on a trampoline stretches and curves the fabric, massive objects like stars and planets distort the fabric of spacetime. This distortion dictates how objects move in the vicinity of massive bodies, explaining the force of gravity that governs the motion of celestial objects. The concept of spacetime leads to a profound and often counterintuitive implication: the block universe. If we envision all of spacetime as a single unified entity, then the past, present, and future must all exist simultaneously within this block. Think of a loaf of bread, where each slice represents a moment in time. Just as all the slices of bread exist simultaneously within the loaf, all moments in time, past, present, and future, coexist within the block universe. This perspective challenges our intuitive notion of time as a linear progression from past to future. In the block universe model, the present moment holds no special significance. It is merely one slice within the vast expanse of space-time, no more or less real than any other moment. This model suggests that the past is not gone, nor is the future yet to come. They all exist within the unchanging framework of the block universe. While the block universe model is a compelling consequence of relativity, it remains a topic of ongoing debate and philosophical discussion among physicists and philosophers alike. One of the most intriguing consequences of Einstein's special relativity is the relativity of simultaneity. This principle asserts that the timing of events, particularly whether two events happen at the same time, is not absolute but depends on the observer's frame of reference. Imagine two lightning strikes occurring at points A and B, separated by a significant distance. An observer stationed exactly halfway between A and B would perceive both strikes as simultaneous if the light from each strike reaches their eyes at the same time. However, consider another observer moving at a high speed relative to the first observer and passing the midpoint at the precise moment the first observer sees the simultaneous strikes. Due to the finite speed of light and the moving observer's relative motion, the light from strike A will reach the moving observer before the light from strike B. This difference in the arrival times of light from the two events leads the moving observer to conclude that strike A occurred before strike B. Therefore, events that are simultaneous for one observer may not be simultaneous for another observer in a different frame of reference. The concept of time takes on a crucial role in our understanding of motion. Velocity, a fundamental concept in physics, measures how quickly an object changes its position over time. The mathematical relationship is straightforward. Velocity equals distance divided by time. This simple equation highlights the importance of time as a fundamental quantity in determining velocity. To accurately describe the motion of an object, we require both the distance it covers and the time it takes to cover that distance. Consider a car traveling 100 kilometers in 2 hours. Using the formula, we find its velocity to be 50 kilometers per hour. This calculation seems straightforward, but it underscores the essential role of time in quantifying motion. Without a reliable measure of time, determining the velocity of an object, or indeed any quantity involving rates of change, becomes impossible. This interdependence of time and motion lies at the heart of our understanding of the physical world.